In this lesson, we're going to look at testing the claim about one mean. Now this will be very similar to what we just talked about, testing the claim about one proportion. The difference will be the distribution that we use to test a claim about a mean and how we use that distribution. But they're still going to have, we're going to have a p-value method and a traditional or critical value method. So first of all, let's look at the p-value method. So the test statistic we'll use when we're testing a mean, a claim about a mean, is this t-distribution, or this t-test statistic rather. X bar, of course, will be our sample mean. Mu is our population mean. S will be our sample standard deviation. And n, of course, is our sample size. So again, we'll need this test statistic no matter if we're talking about the p-value method or the critical value method. And again, our p-value is the area or the probability of getting a test statistic at least as extreme as our test statistic, but possibly more extreme. In other words, it's the area in the tail to the right of a positive test statistic or the area to the left of a negative test statistic, or twice that of either one of those if this is a two-tail test. So let's look at this example. A boat company claims that the mean weight of men is 166.3 pounds if we take a random sample of 40 men and find that the mean of those 40 men is 172.55 pounds with a standard deviation of 26.33 pounds. Test the boat company's claim. So first of all, just like with the testing a claim about a proportion, we'll identify the claim. But of course, this time we're not testing a proportion, we're testing a claim about a mean. So the claim was that the mean weight of men is 166.3 pounds. So that is, the mu will equal 166.3. And the opposite then is not equals, so the mean does not equal 166.3. Step 3, just like before, is identify the null and alternative hypothesis. And again, since the equal sign in this case is with the claim, the null hypothesis will go along with the claim, and the alternative hypothesis will go along with the opposite. Since the alternative hypothesis has a not equals, we know that this is a two-tail test. So now let's calculate the test statistic using this test statistic formula, where in this case x bar is the 172.55 pounds, and our mean, population mean rather, is 166.3 pounds. S in this case, our sample standard deviation, was 26.33 of a pound, and our n, of course, was 40 since we sampled 40 men. So throwing all this into the formula, we get a test statistic of about 1.501. So notice I'm taking this out to 3 decimal places now, mainly because the distribution sheet that we have for t-distribution, all those t-scores have 3 decimal places. So I'm just being consistent with those. But if you took it out to 2 decimal places or 4 decimal places, that's fine. So next we'll find the p-value with the student t-distribution table. You can also find the p-value with Excel if you want to know the exact p-value. But in this, we can find just an estimate of the p-value using the t-distribution table, which is good enough if we're just comparing it to find out if it's less than or greater than the significance level, because that'll tell us whether to reject or fail to reject the null hypothesis. And that's all we really need. So since our test statistic is positive 1.501, and we want the area to the right of our test statistic. And since it's 2 tails, we're going to look up the area in 2 rows, or excuse me, in 2 tails row on the t-distribution table. So that is, I want to first find my degrees of freedom, which since our sample size was 40, I'm going to go to the row 39 and look up 1.501 in that row. But of course, notice 1.501 is not in there. but 1.501 is between 1.685 and 1.304. So in the area and two tails, that tells me my p-value is between 0.1 and 0.2. So I know my p-value is between 0.1 and 0.2. Now I just have to compare this to my significance level to decide whether or not we reject the null hypothesis or fail to reject the null hypothesis. So since our p-value is greater than 0.1, we know it's greater than our significance level of 0.05. Now you may be asking, why did we use 0.05 for the significance level? Well, the idea is that if you're not given a significance level in the original problem, 0.05 is the most common significance level, so we're just going to use that as a default. So because we know our p-value is between 0.1 and 0.2, we know it's greater than 0.1. And if it's greater than 0.1, it is certainly greater than 0.05, and since the p-value is greater than our significance level, 0.05, we fail to reject the null hypothesis. So now interpreting that result, let's look back at the original stuff we did, identifying the claim. Since we failed to reject the null hypothesis, let me cross out my alternative, which went along with the opposite, and that means we can indeed support the claim. So my interpretation is that there appears to be enough evidence to support the claim that the mean weight of men is 166.3 pounds. Let's look at this example. A simple random sample of 25 filtered 100 millimeter cigarettes is obtained and the tar content of each cigarette is measured. The sample has a mean of 13.2 milligrams and the standard deviation has a standard deviation of 3.7 milligrams. We're going to use a 0.05 significance level to test the claim that filtered cigarettes have a tar level below 14.6 milligrams. That happens to be the tar level of unfiltered cigarettes. So what do these results suggest about the effectiveness of the filters? So first of all, identifying the claim, we want to test the claim that filtered cigarettes have a tar level below 14.6. So that is, mean will be less than 14.6. The opposite then, the opposite of less than, is greater than or equal to. So now to identify the null hypothesis, think about which one has the equal to sign in it, in this case the opposite. So that means our claim will correspond to the alternative hypothesis, and our opposite will correspond to the null hypothesis. So our null hypothesis, of course, is the mean equals 14.6, but since the alternative is less than, we know we're dealing with a left tail test. So now let's calculate the test statistic for this sample. The mean from my sample, my x bar, was 13.2 milligrams. Mu, in this case, of the population or assumed milligrams, tar level rather, is 14.6, which we can get from the null hypothesis. S in this case, of course, is 3.7 milligrams, and N, we sampled 25 filtered cigarettes. So throwing all this into the calculator, we get a test statistic of negative 1.892. So let's identify the p-value now. First of all, since we have a negative test statistic, but the t-distribution sheet has only positive t-scores, we're going to consider our test statistic to be positive when we're looking it up, but keeping in mind that it's actually negative. So we had a sample size of 25, which means I'm going to be in the row 24, degrees of freedom, and I want to know where my test statistic would fall. And since the positive version is somewhere between 1.71 and 2.06 in this row, then I can say that the p-value is somewhere between 0.025 and 0.05. And notice I'm looking in the area in one tail because this is a left tail test, not a two tail test. So my p-value is somewhere between 0.025 and 0.05. So since the p-value is less than the significance level of 0.05, keep in mind I don't know exactly what it is, but I do know it's less than 0.05, which is our significance level. So I can reject the null hypothesis. So again, to interpret this, go back to the claim and we can reject the null hypothesis, which in this case means that we can support the claim. So that is, there does appear to be enough evidence to support the claim that filtered cigarettes have a tar level below the mean tar level for unfiltered cigarettes, which is 14.6 grams. So based on our sample, it does look like the filters have some effect on the amount of tar level that gets into the lungs. So now let's look at a couple examples using the critical value method. This again will be very similar to what we did when we were testing a claim about a proportion. It's just slightly different because we're using a different distribution. The US Mint has a specification that pennies have a mean weight of 2.5 grams. A sample of 37 pennies manufactured after 1983, when they changed the metal makeup of coins, has a mean weight of 2.4947 grams and a standard deviation of 0.01648 grams. Use a 0.05 significance level to test the claim that this sample is from a population with a mean weight equal to 2.5 grams, which, of course, what we're doing is testing to see whether this sample came from an actual set of pennies that corresponded to the specification by the US Mint. So we'll be able to answer the question, do the pennies that are in this sample appear to conform to the specifications of the US Mint? So first of all, we'll identify the claim. The claim is that this sample is from a population with a mean weight equal to 2.5 grams. So mu will equal 2.5, which means the opposite is not equal. Mu does not equal 2.5. So of course the one that has the equal sign corresponds to our null hypothesis, and the other one, the opposite, in this case, corresponds to the alternative hypothesis. Since the alternative hypothesis has the not equals, we know this is a two-tailed test. I've got this on the wrong spot. It's because the alternative hypothesis is not equals that we know this is a two-tailed test. So let's calculate the test statistic for this sample. X bar, of course, will be 2.4947, and mu will be, from the null hypothesis, 2.5 grams. S in this case, of course, is 0.01648, and N is 37. So throwing all this in, we get a negative 1.956. So now let's identify the critical value corresponding to our 0.05 significance level. 36 degrees of freedom, and keep in mind this is a two-tailed test, and then we'll compare it to the test statistic, negative 1.956. So our degrees of freedom should be 36, which is 1 minus our sample size. And since the significance level is 0.05 in two tails, I just have to find 0.05 in two tails to tell me which column to look in. Go down to the 36th row. That tells me the critical values are 2.028 and negative 2.028 because this is a two-tailed test. So I want the critical values on both sides of my distribution. So since our test statistic is negative, we compare it to the negative critical value. Negative 1.956 is not further to the left than the critical value, negative 2.028. So our test statistic is not in the critical region, which would be in the left tail. That means we fail to reject the null hypothesis. So in general, if our test statistic is greater than the positive critical value, we would reject the null hypothesis, and if it's less than the negative critical value, we would reject the null hypothesis. But in this case, our negative test statistic is not further to the left or less than the negative critical value, so we fail to reject the null hypothesis. So with this in mind, If we fail to reject the null hypothesis, we can cross out the opposite, which means there is enough evidence to support the claim that this sample came from a population with a mean weight of 2.5 grams. And therefore, it appears that these coins do conform to the specifications of the US Mint.